Hi everyone, this is the first lesson of Vertex AI pipeline tutorial, and it will be about ML basics. So we are going to train a model using Xgboost library and use scikit-learn for feature preprocessing. If you're familiar with them enough, feel free to skip it and go directly to the second lesson. Just use the code in video description below. We are going to train a model to distinguish dwarfs from goblins using some continuous features like height and weight, and categorical features like weapon type. So let's think about how they're different for dwarfs and goblin. Dwarfs' height is about 4.5 foot, and weight is about 150 pounds. Weapons they use mostly is axe, hammer, sword, and less likely a spear and a bow. Goblins will have average height of, let's say, 5 foot, but let's make it with more variance. And weight will be slightly less in average, but also have higher variance. And weapon type, it's gonna be, let's say, a bow, then a spear, and still sword. Slightly less likely hammer and an axe. And if we take a look in distribution, this blob is for goblins, and the blue one is for dwarfs. So dwarfs are more localized in the bottom right area of the chart. And on the legend you can see the different weapon types. So each marker is responsible for different weapon type here. So let's generate the input dataset for dwarfs. So we'll use normal distribution for continuous features, and we'll generate the height here and weight here using the parameters we already defined, and we'll use weighted random choice for weapon types. So we have weapon types like axe here, and the probability that the dwarf will use axe is here. And we have two lists matching, so weapon types and their probabilities. And let's do the same for goblins. Yeah, very similar for goblins. The only difference is we have slightly different parameters for continuous features and different weights for weapon. So as you can see, the weapon for goblins is more uniformly distributed. Meantime, for dwarves, we assume that they use much more axe and hammer and everything else much less, especially when it comes to bow and spear. Once we generated the data, we combine everything into pandas data frames. So this is our dwarf data frame, this is for goblin, and this is our output result, which we make by combining those two. Before training the main model, let's do some analysis. Our data is three-dimensional. We have height, weight, and weapon. And we can use t-SNE to reduce dimensions. And once we plot, we can see how much groups of different combinations overlap between each other. If we see a lot of overlap, Xgboost library probably won't be able to perform well. To train t-SNE model, we first need to preprocess features, and we'll use column transformer class from scikit-learn to apply different transformation for different columns. So we have height and weight continuous features, and we'll use standard scalar for them, and we have weapon, and we'll use one-hot encoder. Standard scalar is an approach when we use normal distribution to scale values between 0 and 1. So first we'll find the mean value, and everything above 2 sigma we consider to be as 1, and everything below minus 2 sigma we consider as 0, and everything in between we scale pretty much linearly. And the benefit of this approach of just regular linear scalar is that it's way more reliable in terms of outliers. So let's say we have a really big outlier somewhere here, it will just ignore because it's above 2 sigma. So it won't affect to standard deviation too much if we have big values outside. So that's why how it will ignore. In case of linear scalar, if we have most of the values over here and we use linear, so I don't know. So that's gonna be 1, it's gonna be 0, and everything here will be in the interval of 0.2 to 0. Let's say 4. And if the outlier is even bigger, that range will even shrink even more. So the picture will be pretty much skewed, so it's not good. Standard scalar is not a silver bullet though, and it has its own like issues. First of all, if the value already is scaled from 0 to 1, we don't have to calculate mean. Moreover, if the distribution of the values is not following normal distribution, it's not going to work well enough. For example, we have most of the values, let's say, around value 73, and a few ones will be around 100. So we'll have just this crazy distribution. So it's not normal distribution. It's like very specific one. So in that case, linear scalar would probably work better because we'll have this boundary as 0 and this boundary is 1, and it will work much better because normal distribution will build a mean value something like here, and standard deviation would be probably looking like this. That happens when your data set is not balanced and you have one of the classes pretty much dominant. That happens also when you want to detect anomalies. So for anomaly detection, some of the rare cases will happen, but standard scalar won't preprocess features well enough. Let's discuss one-hot encoder. One-hot encoder will create separate columns for each of the values for categorical data. We have the column called weapon, and for each of the data it will create a separate column. So weapon column, and for the value x it will create a column called weapon x, and it will put either 1 or 0. So for the bow it will create one more weapon bow and also put either 1 or 0, and etc. Then we combine both preprocessor and t-SNE model inside one pipeline, and that is going to work like a model itself. So when we call fit transform, it will both train the t-SNE model, run the data preprocessing, actually vice versa. It will run data preprocessing, then train the model, and then it will do the inference and spit out the output as a data frame here. If we plot the output of t-SNE model, we can see a two-dimensional chart. We had 3 dimensions: height, weight, and weapon type. Now we have some internal dimension, like embedding dimensions of the t-SNE output. And we see that the data is pretty much separated already. So the model, Xgboost model, will be trained pretty well. Let's see, this is the dwarfs blob, another dwarfs blob, and here, and this one is almost only goblins, and here as well. Now we can train the actual model, and first we need to prepare the dataset. We do need a creature as the output. So we extract it as our result, which will fit for Xgboost model to learn. In case of t-SNE, we just ignore this entirely, and we just use those 3 input parameters to reduce the dimensions. Then we split the dataset in test and train, and the same for the output. And those data frames we can use as inputs for Xgboost model. We can do the same data preprocessing as we did for t-SNE, with only addition that we also train the label encoder. And we make this label encoder as part of the pipeline. So let's take a look. This is the pipeline. We have a preprocessing step. We have the model itself. And we use a custom class called label encoder transformer from Orient Express library to use this label encoder to spit out the concrete category as a string rather than the ID. So it's convenient because we're going to serialize this model eventually and put it in model registry. And when we run this model, we don't want to additionally somehow provide the label encoder. So we want this label encoder to be a part of the entire pipeline, so we can just deploy it and don't worry about transforming data back. And then we call fit, pipeline fit, and that will actually train our model. Before moving to the deployment step, let's evaluate the model. So first we run the inference on the test dataset and use standard function from scikit-learn to generate a report with precision and recall. So here's the output. So all the necessary scores are there. Xgboost library also provides a very convenient feature, printing feature importance. So we can plot the feature importance, and here how it looks like. So we can see height and weight are the most important features, but also if we see that the weapon is spear, it still valuable information. The reason is dwarves do not use spear, and if it's a spear, it's probably a goblin. The same for bow. Let's summarize what we got. So first of all, it's a preprocessor. Which has one hot encoder. And normal scaler. Then we have XGB classifier. and label encoder transformer. And all of them are packed in one single object pipeline. So once we want to run the inference, we call pipeline predict, and we pass the input data frame. So what happens? The data frame first goes to preprocessor, where we convert with normal scaler the continuous features, and we map the classes to class IDs. Then we pass this data into XGB classifier, and the classifier generates the predictions. Then we pass the output to label encoder transformer, because the classifier returns the output in the form of class IDs, but we want something more meaningful. In our case, it's going to be a dwarf or goblin. For just dwarf or goblin, we could use a single binary value, like is dwarf equals 1 or 0, but in this example I wanted to show what to do if we have multiple classes. So with label encoder transformer, we can potentially have like hundreds of classes, and they can be pretty dynamic, because label encoder transformer is being trained from the output dataset. So this pipeline object in the next steps will be used for deployment and for the inference. The next step, we'll serialize it and upload to model registry and discuss the different ways of deploying the model. Let me know if you have any questions, and the second video will be available soon.